We are on for today.
Day 18 of our long journey.
Day 47.
So, open up your notebook to a brand new section. We've got the start of the second semester.
Wait, like a brand new section or just like a new page?
Whatever. I just want you to make sure that there's a break. You can see the break between the two semesters. Yeah, big bold. You have a lot of tabs. So everybody should start at the top of a brand new page. That way we're all on the same page.
We all have different pages. I got it. It wasn't your best one.
No. That's not saying much though.
You got unaccustomed to that.
It's been a while since we've done the Swivl. Okay. Well, today is a very exciting day in calculus because we're going to learn about the fundamental theorem of calculus today. Okay, you can see the orange packet that you have in front of you. We're going to spend the remainder of the week on this packet. You're not going to get a new assignment guide until Monday, okay? Because that's when we're going to start to do it. So what I like to do for each new unit is spend a couple of days just explaining the concepts behind everything so that you can, then you know enough so that when we actually start doing some skills that you've got a feeling for what's going on. So what we do in second semester is pretty amazing, and it's pretty funky, but at the same time, it's actually pretty simple. It's a hard thing to describe. So what I'd like to do is, first of all, relate it to something that we've been doing before, and then we're going to see how it can be applied to the things that we're going to do in the future. So the big focus for the semester is the fundamental theorem of calculus. Okay. So I'm going to tell you what it is, but I'm going to kind of try to weave it in with the several different concepts. There's like a lot of things that have to get tied together. So at least to get off the ground, we have to talk about lots of different things all at the same time. So let me just give it to you outright what it is, and then we'll start looking at what the heck that it means. Okay, I'm drawing what's called the integral symbol. Okay, it's a big long S. Okay, and it looks like an S because it actually comes from the word sum, as in adding stuff up. And so this is the integral symbol. So look at this. This is how it's spelled. Symbol. Okay, that's what that is. Integral. And A and B here are just numbers, and I'll explain what that is. So the notation looks like this. And it's going to look foreign to begin with, and that's okay. Because anytime you try something brand new, you pretty much suck. But that's okay, because that's normal. That's okay. Because you only get good at something after you start doing it many, many times. And lo and behold, this thing here is equal to this. Okay? That's the fundamental theorem of calculus right there. Okay? Now, what the heck does it mean? Okay? That's where we're going to go to. The first thing I'm going to point out is you should see that this has got a f prime of x right here. And over here, this is an f of b and an f of a. It's not f prime. Okay, so this is f prime. This is not f prime. Okay, it's just regular f. Where we know that the derivative of f of x is equal to f prime of x. And this is sort of a note in addition to the fundamental. The derivative of f is f prime. Bless you. All right, so where do we start? Well, I'm going to try to start with something that you can already relate to, and going to try to challenge you to think about what's actually going on. So let's do some recalling. Okay. So if I say to you, we're going to be given an f prime graph. Okay. And I'm going to say the f prime graph looks like this. Okay. This is the graph of f prime. And I'll just put some letters on here. This is from A to B. Okay. And I ask you, let's put A, B here, and let's put C here. Okay. And these are the points of intersection on the axis. Okay. So you guys have done a ton of problems like this. Okay. So if I say to you, this is the graph of f prime, tell me about f. Yes?
Increasing from A to B.
Everybody agree with that? And why is that?
Because f prime is greater than 0.
Perfect. Okay? So we can say, therefore, f is increasing on the interval from A to B because f prime is greater than 0. And remember, technically, the finish to this is f prime is greater than 0 on the open interval from A to B. That's like the true reason, but that's not required on the AP exam. That solves the problem of f prime being equal to 0 on those endpoints. Okay, then what else are you going to tell me about f? Yes.
F prime is decreasing.
Careful. Say it again.
F prime, f is decreasing on A, B, C, because f prime is less than 0.
Okay. There's not a person in the class that shouldn't be able to identify that. Okay. That's a fundamental component of what we did first semester. But now here is the question. This is key. Now I'm going to ask, how much did f increase on the interval from A to B? We know it's increasing, but how much did it increase? Yeah. Okay. This is the key concept here. The answer to this question is the area that's bounded by f prime and the x-axis. Okay? So the answer is the area found, let's say, the area bounded by f prime and the x-axis on the interval from A to B. Okay. So, to make a little note here, this area right here, the area is equal to, hi. Yes. Okay. Mary Kay. Sorry. I just had to. Mary Kay, that's what you're going to be called now. Okay, the area is equal to the amount of increase in F. Okay. So everybody got that? Okay. Okay, so we asked the second question. How much did F decrease on the interval from B to C? Since we know that F is decreasing from B to C, how much did it decrease? Okay, finally, somebody. So, not so much that. She asks, how do you figure that out? How do you know what that is? Okay, that's the first question. The second question, which I'm waiting for someone to ask, and the answer is here. Again, it's the area bounded by F prime and the, oops, I didn't put the x-axis here. Make sure you see this. It's the x-axis on the interval from B to C. This concept is huge. Huge. So, again, I'm going to shade this area right here. And we're going to point out the fact that this region, whatever that area is equal to the amount of decrease. In F, and the key thing is that it's in F on the interval from B to C, because we're identifying that as the interval. Okay. So first semester, we identified curve sketching rules that we know where a function is increasing or decreasing based upon F prime. Now we're saying that, you know what, there's a hidden secret in here, and the secret is the fact that the area that is bounded by each one of those regions tells you the amount of increase or decrease. Okay? So two problems arise. Number one, how do you figure that out? And two, how do you know it's right? Am I lying to you? Harry, are you lying?
I don't think so. The orange packet.
The almighty orange packet says so. Because you should always believe everything that's in print.
I'm writing in pen, so I really hope not.
It's good we're not using stone tablets. When is something true, people? When you believe it to be true and when you, or if you prove it to be true. Okay? Have we proved anything? No. I just told you what Harry told me. Says that, you know what, the area under the curve, that's what it is. Why is that, Harry? No idea. We think we briefly talked about it before. Okay? So this concept was actually discovered by Newton and Leibniz both at the same time, which was pretty amazing. I was friends with both of them, and it was crazy. You know, I was like the middleman, telling me this and telling me that. It was amazing. So they each thought they were right. So I want to try to figure out if we can actually figure this out. So what we're going to do is we're going to try to prove that that works. And one way that you can, if you have a problem that's a pretty difficult problem, you start simple. Okay? So here's what we're going to do. We're going to start simple, and we're going to see if we can prove that theorem up there by way of examples. Okay? So these are examples to prove the fundamental theorem of calculus, FTC. So we're going to start with an easy one. Okay? Let's let f prime equal, I don't know, let's let it equal 2. Okay? And I'm going to let my interval be from, I don't know, 1 to 5. Okay? So let's sketch this, and we're going to see if this whole thing works. So 1, 2, 3, 4, 5, and 1, 2. So I'm going to graph f prime. F prime of x is equal to 2. That's what I'm telling you. So if I say, let's focus on the interval from 1 to 5, would everybody agree with this statement? F is increasing on the interval from 1 to 5 because f prime is positive. Everybody agree with that? I mean, it's so easy, it's almost hard, because the function is increasing all the way, it's positive throughout this whole thing. Okay? So today we're asking this: how much does f increase from 1 to 5? That's the big question today. Well, according to our fantasy rule here that we don't know if it actually works, the fundamental theorem, it would be the area under the curve from 1 to 5. So let's do that. Okay. Apparently, because this is what I drew in the last one, this area is equal to the amount of increase on f for the interval from 1 to 5. That's what it's saying. Okay? Can we compute that area? Yeah, it's a rectangle. This part's not magic. Okay, so the area is equal to what? 1, 2, 3, 4 times 2. The area of this is 8. Okay? So what does this say? This says that f must increase by 8 units on the interval from 1 to 5. Do you agree with that statement? You got to make sure that you're checking my work here, because we're trying to prove whether or not that thing is legit. We don't take word for it because someone else said it. Okay, we take word for it when we believe that we have proved that it is correct. Okay. Where do we go from here? Graph it. Graph what? Possibilities of f. Okay. So notice that we're given f prime of x is equal to 2. Is it possible for us to figure out what f of x is? Okay. So this is huge here. This is f prime. Okay. So what we're going to say is the antiderivative okay, and what do you suppose the antiderivative is? It's the function whose derivative was given. It is if you go backwards, if you start with f prime and then you say this. So the antiderivative of f prime of x equals 2 is f of x equals what? 2x plus, we're going to use the letter c. Okay. The c represents the fact there's a constant that could exist here because there's an infinite number of functions whose derivative is 2. 2x plus 1, 2x plus 2, 2x plus 3, 2x plus pi, whatever. Okay? So the question is, how can we prove this part right here? We made a pretty bold statement that said that f must increase by 8 units from 1 to 5. How do we prove it? Does it matter which f of x? Does it matter what c we pick? That's the problem. No? Okay. So let's do a bunch and see what happens. Okay. So f of x is equal to 2x plus 5. Let's pretend I want 5 to be the c. Okay. How do we figure out what f increases, how much f increases if my function is 2x plus 5? F of 5. So we compute f of 5, and we compute f of 1, and then we subtract them. Okay, need your help here. What's f of 5? 15. F of 1? 7. How much did it go up by? Went up by 8. So it increases by 8. Which is exactly what we said here. Okay? Well, that could have been just a fluke. So let's do another one. F of x equals 2x minus 3. Because the c can be negative too. So f of 5 equals f of 1 equals. So what's f of 5? Huh? 7. What's f of 1? Negative 1. Subtract. 7 minus negative 1. 8 units. So change in f of x on the interval from 1 to 5 is 8. In fact, watch this. If I write this as f of x equals 2x plus c, what is f of 5? It's 10 plus c. What's f of 1? 2 plus c. Subtract 8 all the time. This proves it in general that it doesn't matter what c value that you pick, it's always going to subtract right off of itself and get the answer. Okay? So what did we just do? We just took the simplest case, just a constant function, and we proved that the area bounded by the curve of f prime and the x-axis told us the amount of increase of f. And we validated it with an exact problem. Okay? Now, pull out your calculator. Oops. Okay, we're going to graph f prime. We're going to graph f prime. And so everybody do y1 is equal to 2, because I'm going to do this example right here. Y1 is equal to 2, and then do a zoom 6. Okay. That graph is doing what I just did right here, okay, with the purple line being at y equals 2. Okay. Now watch this. On your calculator, you're going to do the second calc. So it's the F4 button, it's the trace button. Do a second calc. Okay. If you go down to number 7, you see there's that little funny integral symbol again. Okay. Press enter. Okay. It's asking for the lower limit. The lower limit is the left-hand limit, which is the 1. So press 1. Then it's asking for the upper limit, which is the 5. And then watch it. What? Okay. Now, not only did it shade it for you, it told you what the answer was. Okay? So, to summarize, and using the notation, need a bigger board. We're going to say this. This is a summary. Okay, watch this. I'm going to use the notation here. I'm going to write the integral from 1 to 5. That's where the a and the b come from. The integral from 1 to 5. Then we put the derivative. See, look back on what's in the purple, or the first thing that I wrote. See, it's f prime goes next. We put in 2 dx. dx tells you what variable is being used. We're using the x variable. Now watch this. The integral from 1 to 2 of 2 dx means it's f of 5 minus f of 1. Two was f prime, remember? 2 was the f prime, that was the derivative. The integral from 1 to 5 of 2 dx is equal to f of 5 minus f of 1, which we did that right here. And the answer to that was 8. You see it? Okay, we're learning lots of new notation and how this is going to work, but this summary here is key because it connects the very first thing that I said with now the very last thing that I said. Okay? And we proved it with a very simple example. Okay. Let's, as long as we got this one, let's do another one, and we can go through it a little bit quicker. So let's do another one. This is a pretty good drawing, I think. You see? Somebody should take a picture of that. It's on the Swivl. Can we do a screenshot on the Swivl?
That's gonna be the new cover page.
Yeah, take a picture of that. I really like that. That's really colorful. Oh, you got to get closer. This has got to be. Come on, no. You got to be straight on. This is like. Okay. I don't even have the heart to erase it now, so we're going to go for it. Okay, let's do another one. So let's do a medium one. Okay. So a medium one, let's make f prime of x equal to x plus 4. Okay, and the interval that we're going to use here, I'm going to try to be tricky here, is going to be from -9 to -5. That's my interval. Okay. All right. Draw the picture for that one. We're going to try to prove the fundamental theorem of calculus using that example. This one's a medium-sized one. Are we going to blow up here? Oh, good. Okay, do you have a picture that looks kind of like mine? The purple graph is the graph of f prime. Okay, this is key. This is f prime of x. And f prime of x is given by x plus 4. The interval that I'm going to do is from -9 to -5. Okay? So, obviously, this is the region that I'm dealing with. So, the first question I ask you is, tell me about f. F is what? Decreasing. Okay? F, don't forget anything you learned first semester. F is decreasing on the interval from -9 to -5 because f prime is negative. Same thing as we always had. F prime is negative. So the question we're asking is, how much does f increase or decrease? That's what I want to know. And where's my answer? My answer is found by finding the area of that shaded region. This answer, the area here, is equal to the amount of decrease in f on the interval from -9 to -5. Okay, what kind of shape is that? Trapezoid. Okay, so the area of a trapezoid is h over 2 times the sum of the two bases. Okay, that's the trapezoid formula. So, need your help here. I need to know the lengths of the two bases and then the length of the height. Okay, so I'll do the hard one. 1, 2, 3, 4. Okay, so how do we figure out the other two lengths? Plug in the x value right here, right? That gives you the y coordinate. So if I plug in a -5, that gives me -1. So this is right at -1. So this length right here is 1. And then what is this length? -9 plus 4 is -5. So that's how far it is down. It's down -5, so that length is 5. Okay, so here we go. h over 2, this is 4 over 2 times 5 plus 1, which is 2 times 6. So the area is 12. So let's wrap this up. Just this statement here. F decreases by 12 units on the interval from -9 to -5. And tomorrow we're gonna finish it. All right, good day.